We have Zach number 1 to quarantine. That was, I'm trying to remember your last name. What's his last name? Is it on the thing? McAllister, that's right. Because Lawless is the mechanical. So Zach McAllister, are you almost back? Or do you have another week to go?
So I should have been almost back. And then a third of my room, the third roommate came down with coronavirus. So now I'm back in quarantine until he finishes symptoms and then 2 more weeks.
Sounds like you need to play practical jokes on your roommate.
Yeah, I'm starting to think of that.
Like, if you're gonna get it, could you guys just get it at the same time? I really don't appreciate that.
Right?
Okay. So we're gonna finish up our momentum, not uniform directional, our momentum equation today. Okay, we're going to do a couple of quick examples, then we're going to dive into the energy equation. So let's see, we'll get hopefully with 2 examples done. So consider plane Poiseuille and Couette. Okay, so I'm going to say what that means if we don't already know. Suppose I have 2 parallel plates. And in this case, the top plate is moving with velocity u. There's a gap h here. And I'm going to call this one x equals 0. This x equals L. Okay, we've seen this example lots. We're going to make it slightly more complicated. And that we're going to add a pressure, dynamic pressure here, P0, and a dynamic pressure here, PL. So you have both a moving plate and a pressure difference, okay, across this gap. And we're going to say that P0 is greater than PL. And we're going to say that it's 2-dimensional. So, we have this long gap in the z direction. So I'll put up coordinates here, x, y coordinate system, okay? So there's this, long thing in the z direction. And we're going to assume that it's steady. Okay. And so if we say it's 2-dimensional, that means dvz, or dvx dz, excuse me, is 0. If we say it's steady, we're going to say dvx dt is equal to 0. And this just means here, if I write down a delta p, then it's less than 0, right? Because if I do p1 minus p0, but p0 is greater than p1, then that goes less than 0. Okay, so if you remember before, we did so this is an example of unidirectional flow, okay, where we've got a flow only in the Vx direction, okay? So we wrote up an equation, rho dvx dt is equal to minus dp dx plus mu v squared vx dy squared plus v squared vx dz squared. We had written this last time for unidirectional flow in Cartesian coordinates in the x direction. Okay. And remember, we found that the unidirectional flow dy was 0, or the vy was 0, and dv was 0. So the other 2 momentum equation were 0. And then the nonlinear term, the v dot grad v term, that was 0. Okay. And we found that it was the dvx dx was 0. So that was another term that would have been here. Okay, so all those terms dropped out. So we're sort of left with this piece, which is pretty simple, but still a PDE. So now if we go to this geometry, we can see we have a few more simplifications, right? So I said it was 2-dimensional, so this guy is 0. And I said it was steady, so this guy is 0. And we're left with 0 equals minus, and now I have total derivatives, dp dx plus mu d squared vx dy squared. Okay, so that's the that's my governing equation. That we did all this work in the momentum equation, right? Now to get down to this that we did in undergrad. Okay, and we have boundary conditions here, so we can say Vx at 0 is equal to 0. So if I roll my 0 on that spot, and Vx at h is equal to u. Okay, so we've solved this problem before separately. Let me get rid of this one. It's out. Okay, so I want to solve this. Okay, and we've solved stuff like this before, but I don't know if we've solved. Did we do quasi-flow in class? I don't remember if we did it or not. We did it in cylindrical coordinates, didn't we? We did. We did it in cylindrical coordinates. Okay, so we have to somehow integrate this. But the issue here is that we have these two terms, right? One that has a derivative with respect to x, one that has a derivative with respect to y. Okay, but we can say that dp dx is equal to mu d squared vx dy squared. That's just algebra. I just moved something over to the left-hand side, right? Added that over, okay? And I can see that that must be equal to a constant. Okay? I can see that for a couple reasons that I can say. The first is that, so this is a derivative with respect to x. I know that pressure is only a function of x, okay? Because through the momentum equations, I showed that dp dy was equal to 0 and dp dt was equal to 0. That was the result of the other momentum equations. So I know that it can't depend on y or z, okay? And Vx, I said it could only depend on y. I said it couldn't depend on x or z. I got that also from the momentum equations and the assumptions of the problem, right? So if that's the case, then these things, you know, if I took the y derivative of this guy, that would have to be that would have to be 0, right? If I took the x derivative of that, that would have to be 0. But their derivatives are with respect to different things, so that means this has to be a constant. Does that make sense? I always find that a little confusing to think through. I always think of it easiest if I took a y derivative of this, that means 0. That means if I integrate it with respect to y, that has to be some constant. And the same thing with respect to x here. And since then I can't depend on x or y, the only thing it could be then is that constant. Does that make sense? Tyler's kind of leaning forward, so I want to see. Does that make sense to you, Tyler?
Not quite.
Okay. I have to kind of write it out. So if I took d dy of dp dx, that has to equal 0. You buy that? Okay. So then if I took the integral of this, it's going to be a constant. Okay. So that's, I mean, that's the key idea. And I can do the same thing with this one, right? But the derivative there with respect to x. And so since I set them equal, they must be equal to the same constant. Okay. So now, yeah, please.
So is it, I mean, I guess maybe that's just a proof, just for the sake of proof. Like, wouldn't it be enough to know that it has to be equal to a constant to know that one side, like dp dx? If you know pressure only is a function of x, then you immediately know that it's equal to a constant.
Yes, that's right. Yep. Okay, I'm just, you know, there's different ways to kind of think it through. So, okay, so now if we know this, okay, we can solve for the pressures. Okay, So the easiest way mathematically I know to look at this is if I know that dpdx equals a constant, then I know it's just a slope, right? The slope is a constant. So I can immediately write down that dp dx is equal to delta p y by delta f. Right? That's pretty easy. So delta p is pl minus p0 divided by l, where l is that distance, right? So that's not too bad. I could also, if I wanted to integrate, use the boundary condition p0, pl, but I'll just get this back out. Okay. So now I can solve for the velocity. P squared dx, py squared is 1 over mu delta p by l. Okay. So now I take that and integrate it twice. So first integral, I can write d of dvx dy equal to 1 over mu delta p over l y. That would be the first integral. This was always confusing when I teach undergraduates. I hope this is really clear to you guys how to integrate something twice. In the undergraduates, I always get people who screw up on the step. I don't know what it is. I don't know. I think it's just calculus is still needs to be worked through somewhere. But like the one that always makes me the most like shudder is that I get people take the square root of both sides. And then I'm like, no. And then the integral gets hard. And then they get stuck on the test. And you're like, it's not really squared, right? That's calculus. Oh, makes me hurt inside. Anyway, so we integrate it once. We're going to get dvx dy is equal to delta p over mu l. Now I have x plus some integration constant, right? When I integrate again, I'm going to get vx is equal to delta p over 2 mu l x squared plus c1 x plus c2. Oh, there was. Oh my goodness. Which one? -5 on my exam. Okay, thank you. Okay, so now I do the boundary condition thing. So plug in Vx at 0 equals 0. That tells me that one's 0 and that one's 0. That tells me that C2 equals 0. Do Vx at h is equal to u. So I plug that in, I get u equals delta p over 2 mu l h squared plus c1 h. Right? So then I get u minus delta p over 2 mu l h squared equal to c1 divided by h on both sides. That's what I get for C1. C1 is u over h minus delta p over 2 mu l multiplied by h. And I can plug that back in this bad boy right there. And we get Vx is equal to delta p over 2 mu l y squared plus, and C1 is u over h minus delta p over 2 mu l h multiplied by y. Okay, and then we can simplify this a little bit. Make it a little prettier. So I can pull out a delta p over 2 mu l. I can pull out, so I can have that one and that one, right? And then I want to pull out h squared, put it on the top. Now I'll get y over h, y squared over h squared, minus, this will have a y over h. Okay, and then I have plus mu y over h, or uy over h. Okay, so I have those two lumping of terms. So if you look at this now, this is the quasi-flow part. And this is the correct flow part. Okay, so if I take that, and I said I had u, the boundary condition was 0, so I didn't have a moving top plate, I would just get the quasi-flow part. And if I said delta P was 0, right, I didn't have the pressure difference, then I just get the correct flow part. And they're just added together. Okay, so that's a problem that we do all the time because it's math is easy. So I think we should be able to do it. Any questions on that guy? Sick of solving pipe flow like problems. No, do you like that one? It was easy. Stick with it. The next one, I think I give this as a final exam question. If I remember. Yeah, it was a homework in fluids. So this one is Couette flow in cylindrical granules. Okay, this is also called a Couette viscometer. Okay, so I've got some outer cylinder, some inner cylinder, okay, and they're going to rotate. They're going to rotate one relative to the other. So in this case, this problem, it's going to rotate in that direction with angular velocity omega naught. So if I think about it, it's going to have some velocity profile like this. Okay, and I'm going to define cylindrical coordinates here as r. That's not r underscore r. And theta will be in this direction, starting at that point there. And I'm going to define this inner radius as kappa r, and the outer radius as big R. Okay, so we go back. We have to be a little careful with unidirectional flow for non-Cartesian coordinates. So I wrote this simplification up of that equation. We can't just take that equation and run with it, right? We got to go back to our Navier-Stokes equation. So Navier-Stokes equation, rho dV dt is equal to minus grad P plus mu grad squared V. And we have del dot V equals 0, okay? And so we're going to try and solve for the steady two-dimensional unidirectional case. So steady unidirectional. And what was the one I said? 2D. Okay. So can just remind ourselves that del dot V, what does that give us? So del dot V is 1 over R. Actually, save us a little time. I'm going to do this. Okay. I'm going to write the simplified equation. I'm going to write this 0 is equal to minus 1 over r d theta plus mu d dr 1 over r r v theta. Okay, I'm going to do this. So if I assume this, I can go from here to here. Let's just think about how that happens. So first, I know that terms that are in del dot v equals 0, they're going to lead to something that's like fully developed, right? So as I go around in theta, I shouldn't change, right? Because if I'm really only going to have a v theta, that's the only, when I have unidirectional v theta only, right? That's what that means. So it shouldn't change as I go around in theta, or else I'm going to have to add mass or take mass away. That's what that's doing. So this is going to lead to something that says dv theta d theta equals 0. Okay, steady, that's easy. That's dv theta dt equal to 0. Let's see, unidirectional says that VR and VZ equals 0. Okay, that's unidirectional means. And then the unidirectional thing also tells me that I have the V dot grad V equals 0 that comes out of this piece, right? That's a consequence of being unidirectional. So what would be good, so you should take maybe 20 minutes after class or sometime before you do your homework and prove to yourself that you can go from here to here. Okay, just doing unidirectional steady 2D. Make sure you understand each term, why it goes away. Okay. All right, so we get to this guy, and that looks a lot like the thing we were messing with before, right? That looks a lot like this here. This thing, okay? Where we did Poisson and Couette flow. Okay, there's an important difference here, though. This term is going to be 0. Why? Who can tell me why? Do you think Mark or Mark? Exactly. It's just a closed fluid loop, right? So I couldn't impose a pressure difference on that spot and then get a pressure difference there, right? That would be weird, right? So the dynamic pressure around the loop has to be 0, right? Okay. So that guy goes away. So now I'm just left with Couette, and I have boundary conditions. So my boundary conditions are that V theta at R equals kappa R, that's the internal one. That has to be 0. That's no slip on the internal cylinder, okay? And V theta at R equals big R has to equal the angular velocity multiplied by R. Okay, that's the velocity on the outer cylinder. So then I plug those, now it's just a math problem from here, right? Integrate this guy 2 times, apply the boundary conditions, okay? It's a little bit of math to do the boundary conditions. Yeah.
What is the V theta equals omega R? That's the velocity on the outside.
You're asking about what that is?
Yeah, what that boundary condition represents.
Yeah, so this is the angular velocity. So remember that a velocity is an angular velocity times the radius, right? So that's what the actual velocity is there.
I think I just forgot that equation.
Okay. Yep. Good question. Any other questions about the boundary conditions or about this? Okay, so I'll just write up the answer then. So integrating twice. Okay, and apply boundary conditions. And you get the following answer. V theta equal to omega naught kappa r divided by 1 minus kappa squared goes there. R divided by kappa r minus kappa r divided by r. Okay. I'll write what the boundary conditions are, or what the constants are to get from the boundary conditions. Just so if you go through and do this, you know, date night, whatever, right? Have a fun time, Saturday, party. You want to impress your friends. You're like, let's keep quick, let's go there. Check yourself along the way. Okay, so C1 was 2 gamma, or 2, I don't want to say gamma, 2 omega naught divided by 1 minus kappa squared. C2 is omega naught r squared, and then minus kappa squared 1 minus kappa squared. Okay, so that's algebra. I want to get to the energy equation for a little bit today, so I wanted to get to that. Okay, any questions about those examples? I trust that you saw the schedule changes. Oh, slowing way down. I hope you guys aren't too mad, but that means your homework's easier for the week.
It's not due on Monday.
It's not due on Monday? Is that what I put on there?
It's on Wednesday.
Isn't it due Monday?
I don't know.
All right, we better pull it up.
You said it was due Wednesday.
It says Wednesday.
Which was
Not the one
nice
I
with a
got.
conference this weekend, just saying.
Are you looking to see real quick? It's not a big deal. I thought I had a different.
Is this the one?
Yeah.
Or this the one?
Oh, and
It's
I did
Wednesday
put Wednesday. I forgot to change that. Okay, that's fine. We'll leave it. We'll just make it Wednesday, but I'm going to put this one back on Monday. Okay, yeah, we'll make it Wednesday because I left that there. But I want the next one still to be due Monday. That was a mistake. So, okay. So I'll fix that. So yeah, but it's only 2 problems, right? Because it's the momentum stuff is all the time. Okay. Oh yeah, forgot about that. I don't know what number we're on. I'm just gonna do energy equation. Okay, so moving on to energy. So the outline is we're gonna have energy transport equations. We're going to talk about the mechanical energy equation. Then we're going to talk about the internal energy equation. They're sensing a theme. It's energy. Then we're going to get to D, the equation of change for temperature. Okay, so it's going to take us all of that just to get an equation of change. Temperature. Let's get a lot of this algebra. I just had to work it out for myself to make sure I felt happy. And then we will talk about solving the energy equation. And then when we do solving the energy equation, we will do A simplifications of, what do I call it here? I guess I just call it energy equation. E is dimensional analysis. I don't think that's going away anytime soon. And C are some examples. Okay, that's the outline for energy.
Yes. So this is basically the energy equivalent of the Navier-Stokes. Is that what we're deriving?
That's right. Right. So we're going to do the full 3D version with all the gory details. Okay. Probably actually skip some of the gory details because it takes a lot of algebra. So good thing to do would be to, like when we do these lectures, you know, a good thing to do is if I skip some algebra, right? Take 45 minutes, sit down, work your way through the algebra, make sure you understand the steps. Okay. All right. Let's really quick get. So we're going to have energy transport equation. Let's do A, total energy. See how far we can get on this guy. Okay, so let's start out on the total energy equation. So just like Andrew is anticipating, right? We're trying to get something like the Navier-Stokes equation for energy. And so we're going to need to get an energy balance and combine that with constitutive laws, right? Laws. And that's going to allow us to have a total temperature equation. So it's going to be a bit until we get to the total temperature equation, okay? But we're going to see why in just a second. So let's try to get the total energy equation first. So again, let's do a 3D balance on a cube. So if I've got some cube here, all right, and I call this point X, Y, Z, and this point X plus delta X, Y plus delta Y, Z plus delta Z. Okay, and I have my coordinate system X, Y, this one should be Y, right? Z. And recall that we have this quantity for energy, E, which is a combined energy flux vector. Okay, and I want to look at the energy flow in and out of that box and do an energy balance. So I want to look at the change in energy at time is equal to energy in minus energy flow out. All right, and so we're going to have terms like Ex at X multiplied by delta Y delta Z that are coming in to that box, right? And we have terms like Ex at X plus delta X times delta Y delta Z coming out of the box. And the same thing for Y direction, and the same thing for Z direction. Okay? And then the energy in the box, I'm going to need to take that into account somehow. So we need to think about, well, what is the energy in the box that I need to worry about? Okay, so we've done this process like, I think a lot of times now. So let's see if I can write up an equation that skips a couple steps to see if we can see where we're at there. Okay, so if I just write up, you know, I'm going to call this 1, 2, and 2. 1, 2, 3. Okay, so d dt of rho v squared plus rho u hat plus rho phi hat. Okay, that's going to be 1. I'm going to write it up and then we'll talk. Is equal to minus ex at x plus delta x minus ex at x divided by delta x minus ey at y plus delta y minus ey at y divided by delta y minus ez at z plus delta z minus ez at z divided by delta z. Okay, and then this is over here 2n. Okay, so what's going on here? I've got the total energy in the box. So the total energy in the box changing in time. This is the kinetic energy, right? mv squared. This is the internal energy. U is the internal energy. It's the specific internal energy. So you have specific internal energy. Okay. Phi hat is the specific potential energy. Okay. In other words, it's mg divided by m. So it's just going to be the g vector. If I remember right. Did I write that down anywhere? G or GH? GH. Okay, so I've got, I have m, right, for the mass, and then I have a rho that survives because what happens in this thing, right? I write down the total energy in the box, and then these come from the two terms that go in and out, right? So this one's actually the out, and that one's the in. And I have the delta y delta z. I divide by the delta x delta y delta z, so I get the delta x in the box. And the same thing here, and the same thing here. Okay? So at the end of the day, I now take the limit as my volume goes to 0, right? So take the limit. As delta x, delta y, delta z goes to 0, and I get the following. dt of rho u squared plus u, rho v squared. V squared plus rho u hat plus rho phi hat is equal to minus dx minus dy minus dz, and that's the same thing as minus del dot e vector. Okay? And I think we're out of time, so we will leave that there. The next time we'll plug in E, we'll get the total energy equation, and then we'll talk about the other guys, where we can get to. All right, have a good weekend. We'll do Wednesday.